Good afternoon, and thank you for attending this session 3 concerning solutions and opportunities relating to the New England Railroad infrastructure. My name is John Unsworth, and I am the retired Chief Engineer of Bridges for Canadian Pacific Railway and currently working with AECOM as a railway bridge design consultant. My experiences with railway bridges, which are often, except of course for the dirt, the oldest part of the railroad infrastructure. Today, I'd like to provide a short presentation on the solutions and opportunities related to steel railway bridge life extension. In the first part of the presentation, we'll briefly look at the size of the problem and then what are modern heavy axle freight loads. Following that, we will review issues regarding the strength and service life of existing steel bridges. We'll also see that the fatigue life is a major concern and look at concepts that may help in prioritizing mitigations or narrowing the size of the problem. And finally, we'll look at life extension in the era of heavy axle freight loads. There are approximately 85,000 bridges in the North American Class I railroad infrastructure for a total length of about 2,000 miles. There are many more bridges when you consider the extensive short-line railroad industry in the U.S. Many of the bridges in any railroad inventory are steel bridges, and many are about 100 years old, with some even 25 or more years beyond that age. The size of the problem is therefore quite large, and railroad operators are challenged with understanding the scope of the problem and finding means and methods of effectively mitigating the problem. The era of modern freight axle loads in North America commenced in the early 1970s with the introduction of robust freight equipment that was able to carry gross rail car weights of 263,000 pounds or greater. Previous to this, rail car weights of between 170,000 pounds and 220,000 pounds were typical. 20 to 25 years later came the introduction of 286,000 pound cars, which are the standard for North American railroad unrestricted interchange. Of course, some individual bridges in the infrastructure may have restrictions on weight, speed, or consist. There are also some segments of the railroad infrastructure that are currently handling rail cars with a gross weight of 315,000 pounds. Nevertheless, the North American Class I railroad infrastructure is typically experiencing both locomotive and rail car axle loads of about 72,000 pounds, which may be a challenge for bridges designed for axle loads of 40,000 pounds to 60,000 pounds many years ago. However, the good news is that because of large steam locomotive impacts due to reciprocating motion of the driving axles and relatively low allowable stresses used in the design of most existing railroad bridges, the strength of existing railroad bridges is often not an issue unless section losses from corrosion have detrimentally affected the strength of load-carrying members. This can be seen by a comparison of the net section modulus requirements for girders of different lengths designed in accordance with various REMA specifications since 1906. It is evident that bridges designed 100 years ago typically have adequate strength for modern heavy axle loads. However, fatigue damage accumulation was not considered in the design of steel railroad bridges until many years later, and therefore warrants careful consideration as part of the challenges associated with the existing railroad steel bridge inventory. The fatigue life, in terms of the magnitude of the stress range, in contrast to the maximum stresses used in strength assessments or rating, and the number of significant cycles of stress range are critically important, as both have typically increased on existing railroad bridges within the infrastructure. The fatigue life of a particular detail is inversely proportional to the cube of the effective stress range in accordance with the well-known Basquin equation. The number of significant stress range cycles is increased by increasing traffic density and affected by the detail or member influence line length and the axle spacing of the freight rail equipment. The graphs here shown here, which were produced by Dr. Stephen Dick, who is part of the session 2, thank you very much, Dr. Dick, illustrate that even for steel bridges designed in accordance with the very old 1906 REMA specifications, modern rail cars typically affect the fatigue life of details or members with small influence lines, typically influence lines less than about 50 or 60 feet long. Likewise, the charts shown on this slide indicate that for modern rail cars, fatigue damage accumulation occurs on details or members with relatively short influence lines. This is shown in red where the fatigue damage accumulation occurs for each rail car in the train, in contrast to longer influence line members where fatigue damage accumulation occurs with each train passing over the bridge. With modern freight traffic consisting of greater than 100, sometimes up to 200 cars, fatigue damage may accumulate on members with smaller influence lines. Therefore, we can attempt to narrow the problem to focus on the remaining fatigue life of details or members with shorter influence lines, such as floor beam hangers in through trusses, and the floor systems of through spans with floor beams and stringers with relatively short influence lines. Also warranting attention are short span beam and girder spans, of course. It's also worth noting that the AAR-TTCI service level fatigue testing of steel railroad bridges in the North American railroad infrastructure confirmed that details and members with relatively short influence lines experience considerable fatigue damage accumulation. And as shown on the charts of the previous slides, members with longer influence lines, such as the cord and web members of truss spans and long span steel girders, do not typically accumulate enough fatigue damage to affect the service life of the member. So, if we're trying to extend the fatigue life of existing steel bridges, we should focus on members with short influence line or bridges with poor fatigue details. These are details that might be categorized as fatigue category D, E, or F in bridge codes. To improve the remaining fatigue life, we can reduce the number of stress cycles, improve the fatigue category of the detail, and or reduce the effective stress range. Reduction of the number of cycles can be accomplished by reducing the number of rail cars by imposing restrictions on rail car axle spacings. However, such mitigations are typically not practical. The first is problematical because of market pressures and operating conditions will not allow for a reduction in rail traffic. The latter is generally not feasible because of the existing railcar inventories. In addition, axle spacing adjustments in railcars might be beneficial to some members, but might be detrimental in terms of fatigue damage accumulation to other members. We can also strive to improve the fatigue detail category by either retroactive or proactive repair strategies. The slide shows how fatigue cracks emanating from a poorly fabricated stringer copes can be repaired by gouging and welding of the crack, grinding, and then the installation of bolted reinforcing plates. It's also possible to improve the fatigue category detail of stress risers such as notches or defective welds through repairs. Poor fatigue details such as welded cover plates and other welded attachments may also be improved through repairs. This slide shows how out-of-plane distortion cracking in the web plate of a girder at the base of welded stiffeners may be repaired by stiffener plate removal, grinding, and the installation of bolted reinforcing plates. This repair also involved the installation of bolted web plate stiffeners each side of the repaired web plate. Other techniques used to improve the fatigue category detail involve the strengthening of riveted connections with modern high-strength, slip-resistant bolted connections, the removal of short discontinuous welds such as tack welds, and the removal of intersecting and overlapping welds, which might create a triaxial stress state and reduce fatigue life. The treatment of welds by ultrasonic impact treatment, or UIT, in the shop or in the field has been observed to greatly improve the remaining fatigue life of some details. Another means of increasing remaining fatigue life is by reduction of the effective stress range magnitude. This may be accomplished by refined structural modeling and analysis, 3D models, and connection models allowing for flexibility, which provide a more realistic evaluation of stress ranges and the stress state of the member or detail. Also, the use of measured stresses for strength rating and measured stress ranges for fatigue evaluation typically provide lower stresses and stress range values than those developed from classical elasticity and strength of materials methods. Operating restrictions on train speed, rail car weight, and train consists may be made to reduce stresses and stress ranges, but are typically not feasible from the perspective of a railroad business, where such restrictions would inhibit the timely and efficient movement of freight traffic. Other techniques to reduce the stress range involve modern railroad technology, such as wheel impact load detectors, otherwise known as WILD detectors, and weigh in motion scales to reduce the incidence of very high axle loads that may cause, accordingly, may cause very high stress ranges. The elimination of rail joints on bridges and the replacement with continuous welded rail, or CWR, also benefits fatigue life. However, CWR on existing open deck bridges requires a careful consideration of temperature-induced movement. If the rail fastener and/or deck steel interface is too flexible, or if the rail fastener and/or steel deck interface is too rigid, it can cause stresses in the rail. Even simple things like ensuring the track is properly aligned over the bridge can assist with stress range reduction. The replacement of fatigue-prone members with short influence lines such as truss hangers and floor systems can extend the fatigue life of a bridge by many years. The replacement members may undergo many significant rail car-induced stress range cycles, but if well designed, will have a fatigue life similar to or greater than the remaining fatigue life of the truss members or girders with longer influence lines that will be accumulating less fatigue damage. This slide shows a project where an 80-year-old truss span had its floor beam hangers and floor systems replaced to extend the fatigue life of the span for many, many more years. To maintain rail traffic, the floor system was replaced sequentially, one panel at a time. This slide shows the stringers and floor beam in the panel being removed. The end connections of the existing stringers in the adjacent panel were replaced to accommodate the whole pattern of the new stringer connections, which were designed to allow for some rotational flexibility. This slide shows the installation of a new floor beam. Note the connection hole geometry that's made for flexibility, and new stringers. There are 4 stringers in each panel for load path redundancy. Floor beam tension zones and floor beam hangers, however, are non-redundant fracture critical elements. The new stringers had flange widths equal to the existing stringers in order to facilitate deck replacement in each panel. Here we see the removal and installation of a floor beam hanger. The dead load deflection at joint L1 was very small, allowing for a simple cable yoke to maintain the bottom chord vertical alignment. Through careful review of fatigue life extension means, this bridge is now set for many years of safe and reliable extended service. A thoughtful evaluation of the strength and remaining fatigue life of steel railway bridges can result in an economical, safe, and reliable extended service life for steel railway bridges in the North American railroad infrastructure. Thank you for your kind attention.